All right, so welcome to our QA session that is organized by SciAm Student Chapter of Western Kentucky University. I am Oscan Ozer. I'm an assistant professor at WKU. We are welcoming today Dhanaraja Kasinathan. If that's correct, tell me it's correct.
That's correct.
Good. Okay. All right. So he's a senior data scientist. So this is, in fact, the second talk in a row that we have been organizing. So we started a new way of inviting speakers to our campus. We are using the power of technology at this moment to connect you. And I just want to say a few words about the future event, which is going to be on November 7th. So we're having Amir from Databricks, and he's a data science consultant. And our talk is scheduled to 4 p.m. on November 7th. Don't miss that. It's going to be as good as this talk, I promise. And I just want to say a few words about the speaker, and I'm going to introduce the moderators to you after all, and then you will start your presentation. All right, so Dhanaraja is working right now at Qualcomm as a senior data scientist, and prior to this position, he worked with a Silicon Valley startup as a data scientist, implementing machine learning algorithms to manage power consumption with data centers. And prior to that, he was with United Technologies Research Center as a senior research scientist, researching and working on optimization and control of high performance buildings. And he was a postdoc working on automotive control with the mechanical and mechatronics engineering at the University of Waterloo. So you stayed at University of Waterloo after you got your PhD. That's good. I didn't know about that though. And obviously he got his PhD from University of Waterloo. His academic mom was my advisor, postdoctoral advisor when I was there. So we were in the same research team at that time. And before then, he held a bachelor's degree in electrical engineering and a MS degree in mathematics from Birla Institute of Technology and Science in India in 2005. And he worked for a few companies beforehand, and he worked as an associate engineer with Broadcom Research India Private Limited from 2005 and 2007. And his interests include data science and big data analysis on addressing problems that arise in data centers, optimizing energy and power consumption, smart grid type projects, control theory, which I'm a big fan of, optimization and control, parallel computing, and control applications in building systems. So that is a very long intro and very long bio. So yeah, so I'm going to introduce you to our moderators. Let me just put that view on Sydney. Can you just stand up? Sydney is going to be the one asking questions, and she is, can you introduce yourself for SciAm? Like, what are you doing for SciAm?
Yes, can you hear me?
Yes, I can, Sydney.
My name's Sydney. Yeah, I'm the secretary of the SciAm Student Chapter, and I'm a senior this year. I'm a math major.
There you go for Jared.
Hey, I'm Jaron. I'm the president of SciAm, and I'm a senior in getting a degree in mathematical economics.
Awesome, cool. Can you also introduce yourselves? I mean, the other SciAm Student Chapter Executive Board members.
I'm Ryan. I'm a senior at Western. I'm a math econ major, and I'm the treasurer of SciAm.
I'm William Petit. I'm going to be taking over as the secretary of SciAm later down the line. I'm just here.
I'm Camille. I'm a senior math major, and I'm the webmaster of SciAm.
My name is Emma. I'm a mathematics and Spanish double major, and I'm the social media officer for the WKU SciAm chapter.
Awesome. All right, so I am now sharing your PowerPoint presentation, and I think you may start anytime you want.
Cool. All right. Thanks for the long introduction, Oz. And very nice to meet with you guys. looking forward for this. All right, so I don't want to. Let's keep all the academic stuff outside and move to the second, maybe not the second slide, but even the third one, because you've basically covered everything that I want to say there.
Sure. All right. Take your time, by the way. Yeah.
Yeah, cool. All right, so this is all about my PhD thesis. I'm just giving you guys a very high level view or like an application oriented view. Stop me if you have any questions at any point of time. So my motivation was to the flight wings. So imagine you're sitting in a flight, it takes off, lands, or it flies in the air. The flight wings has a lot of disturbance, like it has a lot of vibrations. Succumb to various factors, air pressure, quality, whatever. But the one of the problems that at least aerospace engineering currently faces is so they typically wanted to reduce the vibrations that is felt in the flight wing, so you have a smoother ride, right? So the picture next, the second picture in the same slide, kind of shows you an experimental view of a flight a fin. So those little square patches are called piezoelectric patches. Those are basically electromechanical devices which knows how to convert mechanical energy into electrical pulses or vice versa. So they are what called as control devices on this. So essentially, in order to reduce the vibrations on the wings, you apply electrical pulses that will counteract those vibrations. So that's the goal. And the picture that you see on the third, on the rightmost side, is a academic version of the exact same setup, except it doesn't look like that shape. But this is what is called a cantilever plate. I'm sure Oz is very much aware of this. Right? So those black things that you see there is kind of like the patches, and you see how like it kind of represents the flight wings in some way, that you see how it's fixed at one end and the other end is free to vibrate, right? Move to the next slide. So the big question that at that point of time I was solving was, if you were allowed to place actuators, which are these control devices, which is a good spot to place? So the problem can be modeled multiple ways, but I was going on a certain class of models. And in this specific one, I was assuming there are point disturbances, right? So this is basically a 1D version of the exact same picture that you saw in the previous slides. The 2D version, this is a 1D version, and the vibrations are usually modeled by partial differential equations. I wanted to keep math and theory out of this slides, so I haven't put any math in this as of now yet. So the vibrations are modeled by PDEs, like I said, and the disturbances control, everything is modeled in terms of a partial differential equation. So what remains is where is a good spot to place this actuator? That was the problem that I was trying to solve. Consider this setup that's shown on the left. So you have 2-point disturbances. A natural guess would be to place it in the center. Oz, can you move to the next couple of slides? So just do like a right arrow. So it turns out your educated guess is not the right answer here. It turns out it's optimal, even if you have just one actuator, place it at the same place as the disturbance. So move one more. You will see, you mind moving one more to the right? Yeah, so you would see like the cost function. Sorry, that's too fast. So on the center is the cost function that's attached with this optimization problem, and it turns out placing at the center is actually a worst spot, and you probably want to place it somewhere where that function is kind of like a bell, but it has like a double bell. Think of it that way. But yeah, so it should be it's kind of hinting towards any spot where the disturbance actually is present. So, and you could see the disturbance, the objective function, or I call it performance here, is 10x if you place it at the center versus at the actual disturbance. So this is all my PhD theory work. And moving on to the next slide, Oz. So here, I then worked on, again, a control and optimization type problem, but on automotive. So in this case, imagine if you are driving on a icy road, which obviously skids. It's kind of similar to how the ABS or electronic stability that we have currently in the automotives these days. The idea is to give the driver the same feel as though he is driving on the dry road, but on the icy road. So obviously the car skids. You can't do much about it, but what you could do is adjust your torques, the what's called the acceleration torque or the braking torque in such a way that you could avoid that effect. So I was able to achieve this with just doing an optimization based control, and it was kind of cool that there was this the picture that you see in the middle. It was the Equinix, the GM machine. It was a project funded by General Motors, so they gifted us this car to actually try out our experiments. And thankfully, I wasn't sitting in the car when the experiment was done, but it was a nice experience though. The picture shows that it wasn't driven on the icy roads, but in winter, this is in Waterloo, and it gets crazy with snow. So it was actually driven in the snow as well and tested out all theories there. Bunch of publications came out, but it was good work. It gave me a perspective of how theoretical work that you do in school gets applied to real world problems. And I mean, you may ask the question, this is still academia, but keep in mind this was funded by General Motors, so there was the like the real world experience there for me. This moving on to the next slide. So then I moved on to United Technologies Research Center, where the research was heavily focused on high performance buildings. By that, what I really mean is you have a huge building, and building usually consumes a lot of power, right? So the goal was to optimize energy or energy consumption, and primarily we were talking about heating and cooling systems. The HVAC is the official word: heating, ventilation, and air conditioning. Carrier is a business unit. A Carrier, you may be aware of, they are the big guys in selling air conditioning systems everywhere. City, like both commercial buildings, office buildings, as well as homes, right? So Carrier was a business unit of United Technologies Research Center, and we were focusing on doing research work for them. And this on the left, the picture that you see is a representation of what's called a fan coil unit. It's essentially the place where, so you're sitting in a room, you have some air vents that blows cold air into it, right? So typically how it works, this shows the internals of it. Say you are in a colder zone, so you wanted heating during the day, right? So hot water flows through the aeromark, the valves, and goes through the coil, and then there's a fan that also rotates, that pushes the hot air out and into the vents. And then there is also a feedback in this where through the other end, the exhaust air comes in through the system. So there is a feedback that goes on in this. Now what happens is, let's say for whatever reason the valve gets stuck open, so then the heat air just keeps blowing and it just doesn't stop, right? And then we came up with a fault avoidance kind of a control system for those units. So what you see in the right is a time snapshot of that. It's around about 9 o'clock in the morning. You have this valve getting stuck open, which is a very common problem that occurs. And one way out for such a problem is to treat it with the fan speed. So if you know that the valve was stuck open at one particular point, which is what you detect using like a controller and a microprocessor and everything, and then once you figure that out, then you apply a consistent fan speed. You don't change it, you just reduce it, reconfigure it so that the fault is avoided to the best possible extent. I mean, it's not possible to avoid all sorts of faults. What if it's like completely open? You're gonna get worse, but it won't be that bad as you can do something about it usually.